Hi, and welcome back. In today's module, we're going to go through fully reversible stresses, and in particular, we're going to look at how to calculate stress concentration factors for fatigue with fully reversible stresses. So the learning outcomes for today's module are to understand the importance of utilizing stress concentration factors in fatigue, and to understand the impact of notch sensitivity on materials in fatigue, and then finally to learn how to estimate a fatigue stress concentration factor. So let's get started. So in fatigue, you have these sudden catastrophic failures that are somewhat brittle in manner. So even if your material is ductile or brittle, you always have to use a stress concentration factor when you're operating in a fatigue condition. So we've gone through a couple of these steps of how to solve entire fatigue problems. We worked through the last part where we looked at how to compare the endurance strength to the fully reversible stress applied to the component. We've now figured out how to determine the fully adjusted endurance strength, and here we're going to figure out how to add in stress concentration factors for components that are in fatigue. So in fatigue, again, the failure is sudden and without warning, and it's critical whether your material is ductile or brittle to use a stress concentration factor. You'll remember that stress flows through an object, and at discontinuities such as fillets or changes in geometry, radiuses, holes, notches, key pathways, scratches, things like that, you get stress concentrating at that point. So in static loading conditions, we use something called a KT, which increased our nominal stress by multiplying it by KT, the stress concentration factor, to get the maximum stress that's actually occurring at one of these places with a discontinuity. So it's helping you calculate the stress that the part is actually seeing due to that discontinuity. And you'll remember that a KT is based off of the type of loading the part is in, so in this case axial loading, and then the geometry of the part, so ratios of diameters and fillet radii are how you calculate KT. And typically engineers use a textbook called Peterson's to calculate stress concentration factors, because Peterson's has all the graphs. Now in fatigue, life is a little bit different. So first off, the fatigue stress concentration factor is referred to as capital K subscript F. And what happens is that certain materials are more resistant to notches and discontinuities. And so in fatigue, we can use a reduced version of KT called KF. So KF is equal to 1 plus Q times KT minus 1. This is, this is right here is the equation for KF. And Q is notch sensitivity. So Q is kind of determining how sensitive this material is to notches and to loads being applied when there's a notch present. Q varies from 0 to 1. If Q is equal to 1, then the material is very sensitive to notches and you end up using the full KT value. If Q is equal to 0, then the material is not sensitive to notches at all and you'll use 1 as your KF value. And again, your fully reversible stress that you'll utilize to calculate, which will be your sigma max, will be KF times your sigma nominal, or sigma nom. All right, so just a little bit more details about the notch sensitivity factor. It changes based off of geometry of the part, the strength of the part, and the material composition. So here's a notch sensitivity curve for steels with an ultimate strength of around 200 KSI. So you can see as the notch radius increases, your Q increases, which makes sense. It gets more sensitive the larger the notch. So there are some charts for notch sensitivity in a number of textbooks. You can also calculate it for steels. This is for steels and bending. There's a Q equation with a factor that can be derived based off, or calculated, based off the strength of the steel, shown here at the bottom, and R is your notch radius. Keep in mind that typically the data for Q is highly scattered. So these equations are derived from data with a high scatter, which means there's some variation naturally in the equation. And you need to capture that and account for that in your factor of safety. So if you doubt the true value of Q, you could be very conservative and you could use KF equals KT. That's a conservative assumption, and in a lot of cases it will drive your weight up. Other resources you can utilize to determine Q include Peterson's stress concentration factors, Shigley's textbook for mechanical engineering design, a textbook called Fundamentals of Machine Component Design, and there's a textbook on metal fatigue that has various Q factors. The golden standard always in fatigue is to test, and so if you go ahead and you look at Mill Handbook 5J, what you'll find is they've run a bunch of tests with notches on the specimens for various metals. So sometimes you can go in and actually find test data for a specimen with the geometry of your component, and that stress concentration factor is then built in. So you can see that here they're saying this is SN curve data for a specimen with a KT factor of 3.3. So it's a notch specimen with a V groove, and then they give you the actual dimensions of the groove right here. So this is your best bet, but it doesn't always happen. And so then if you're not able to use the data, you can estimate Q using one of the textbooks or using these equations. So again, when you're going through fatigue, what we've learned is how in static failure we learned how to calculate the stresses at critical points. Now you know the equation to use the to calculate the fatigue stress concentration factor, and then you can say the sigma max fully reversible is going to be your KF times your sigma nom, which is nominal fully reversible. You've already learned how to determine the fully adjusted endurance strength, and you now know how to compare your endurance strength to your fully reversible stress. So just to give you guys a good overview, in the next module, we're going to work through this example to figure out the fatigue stress concentration factor for this part that we've been looking at. So again, it's a simply supported rotating shaft and bending. Here it says the fillet radius at all points is R equals 0.1, so there's actually a fillet built in here with a radius of 0.1. And it says that the ultimate strength is 240. It's made out of 5 chrome moly vanadium aircraft steel, and then they give you the stress concentration factor diagram here to the right. So before next time, you guys should go through and try to work through this example where you find the fatigue stress concentration factor at point A on this component. And then we'll work through the example next time. And that's it for today. So I'll see you next module.